Example. You have to notice the tangent to the power of -1x is the arctangent function, which is the inverse function of the tangent. You really need to have some experience to know that the derivative of the arctangent of x is 1 over 1 plus x to the power of 2, and that's why the u in this case here is tangent to the power of 2 -1x, and the du is dx over 1 plus x to the power of 2. It is quite a difficult example, because usually when you have a function over a function, you are expecting that the bottom function will be the one that is the composite one. But now we don't have composite functions here. We have a product of two functions. One is the arctangent of x, and the other one is 1 over x to the power of 2 plus 1. So when we write it like this, obviously it's much easier to notice, and now because of the substitution of the u, the dx over x to the power of 2 plus 1 is just the du, so we get a very easy integral right now, that this is just the integral of u du. So this is u to the power of 2 over 2 plus c, and the only thing left to do is to substitute back the tangent -1 of x, and we get that. Let's see another combination of those two. So now it's the integral of dx over x to the power of 2 plus 1 times the arctangent x. Obviously, we have to do exactly the same as before. It's just that now we're getting the integral of du over u, which is ln of absolute value of u plus c. So we are replacing the u again by the arctangent function, and we get that. We are now going to evaluate these three integrals here. The first one is straightforward. You just have to know that the antiderivative of this is the arcsine of x. What about the second one? We have few options here for a possible u substitution. One of them will be x to the power of 2, and it's not going to work, I'm telling you. And the other one is 1 minus x to the power of 2, which will work. And the other one is to take the radical of 1 minus x to the power of 2. When you try all those as du, it's really about the du. If the du is still there, you can go and this is the right substitution, but if not, it's not. So I'm going to show you what to do here, but there is a place for confusion. But just don't be stubborn. You decide what is your u, and then you try to translate the integral to an integral of the u. If it doesn't work, you have to change your mind. In this case, we should take u equals 1 minus x to the power of 2. So du is -2 times x dx. Why this is going to work? Because if you look, if I will take away the radical of the u, then the leftover in this integrand is x. So if I have x dx, now I really can get x dx as some constant combination of the du. X dx is negative du over 2. So I have this negative half, and then I just have an integral of du over radical u. If you successfully can write an integral of the u only, it means that your u substitution is the right one. Okay, so now we have to continue a little bit. We will have to use the power rule for integrals, so I have to express this as u to the negative half. Now I'm just going to take the antiderivative, well, simplify a little bit, and now I just have to replace u by 1 minus x to the power of 2, and I get that. Here is a really difficult problem. First of all, this is the same u substitution as before, so du is exactly as before. But now I see that the du will take only part of the leftover, The leftover is x cubed dx, but I can only take into the du x dx. So the first thing to do is to split x to the power of 3 to x to the power of 2 times x. So I know what to do with x dx, and I still stuck kind of with x to the power of 2. So every time when I lost and I don't know how to express something as a u function, I should go to my translator. My translator is u equals 1 minus x to the power of 2. So now I realize that if u equals 1 minus x to the power of 2, then x to the power of 2 is just 1 minus u. So now I'm going to replace this by 1 minus u, and I'm going to replace this by negative du over 2. So as usual, we will use the constant rule, and we will have negative 1/2 here. Okay, and it's 1 minus u du, and don't forget to substitute also u for the 1 minus x to the power of 2 in the radical in the denominator. So what to do now? Now I just have to distribute, and I can get that. Now, when I have this, I will have just to integrate each one of them. So this is this one. As you recall, we just did this one a second ago. Okay, so I don't need to go and bother with that, really. And what about the second one? The second one is just the power rule. Well, you can also use the power rule for the previous one. I don't care, but since we did it, why not just to copy the answer? So we will clean out the algebra a little bit, and we will substitute 1 minus x to the power of 2 every time when we see u. And we get that. Example, the integral of x times x plus 1 to the power of 10 dx. This is a really problematic one. I really don't feel like expanding x plus 1 to the 10. And I cannot really distribute anything here because it's to the power of 10. But also, if I'm thinking about this, if this integral was x to the power of 10 times x plus 1, then there's no problem. I can multiply out, not a biggie. So what is the real problem here? The problem is not the high exponent. The problem is the plus 1 in the x plus 1 to the 10. In mathematics, it's very easy to solve problems. Oh, I don't like the x plus 1. I'm just going to call it u. So u is going to be x plus 1. Now we'll bother with the rest. So du is dx, but I still have to write this as a function of u. But if u equals x plus 1, then x is u minus 1. Now when I have this, you realize that I really should not bother by the high exponent, because now I can distribute, and I get that. And this is really easy. Now, substitute instead of the u, x plus 1, and I'm done. As you can see with technique of integrations, when you have the idea, it's really easy to do. The problem usually is what to do. Now we'll take something that is really similar to the one before, but now we know already what to do. Again, the problem is not the high exponent, but it is the negative 1. Because I just want to show you, if you have x over x to the 10, then it's really easy. Again, my u this time is going to be x minus 1. So du is dx. And now what I have to do is only take care of this guy here. But if u is x minus 1, then u plus 1 is x. So now I'm getting this one. This is an easy integral. I have one amount in the denominator, so I can distribute. So I can split these to two fractions. And I get that. Now I should write it like this because I will need to use the power rule for integrals. Now I'm getting this one. I can simplify this a little bit. And the only thing left to do now is substitute x minus 1 instead of the u. And I get that. The last problem in this section is a real challenge one. We would like to show that those two integrals are equal without evaluating them. So I'm going to start with the first one, and at some point we will get to the second one, and then we will figure out that they are really the same. So after the discussion of before, it's pretty clear that the u substitution here has to be 1 minus x. So du is negative dx. So as before, I have to make sure that I know what is x. But if u equals 1 minus x, then x equals 1 minus u. So after this u substitution, I also have to make sure to translate the limits of the integration. In the first integral, the limits are for x. When x equals 0, u equals 1 minus 0, which is 1. When x equals 1, the u equals 1 minus 1, which is 0. So I'm getting a u integral which is exactly this one. If you noticed, I have this minus sign here. If I like to get rid of this, what I have to do is to switch the limits of the integration. So I'm switching the limits of the integration, and I get an integral between 0 and 1 of 1 minus u over u to the power of 1000. This is weird because if I really look up, I see that I already have the integral that I wanted to have, but instead of x I have u. And the thing is it really matters? The answer is no. This is the finite integral. So when you substitute numbers, you get the numbers. It does not depend on the variables, which can be any letter. So maybe it is surprising, but not so. U is just a dummy variable. It can be replaced by any other letter. This integral equals exactly to this, equals exactly to this, or to this one. Why? Just because it's a definite integral and the upper and the lower limits are numbers. And the answer is going to be a number no matter what is the variable. So, this is really this one. And I showed that the first integral equals to the last integral, exactly what I wanted to show.